Now, dear student, chapter number 10, Mechanical Properties of Fluids. And today we have the topic for the discussion that is called the Bernoulli Principle. And in the previous lectures, already we have discussed the concept of the equation of the continuity that makes the conservation of the mass. So the amount of the liquid is flowing through a varying, through a pipe of the varying cross section is the same. That means it's entering inside the pipe is equal to the amount which is leaving the pipe. Okay. And same how we have also discussed the concept of the energy those are available in a flowing liquid for the streamlined flow. That means per unit mass, per unit volume, and per unit weight. Okay. So what is the statement of the Bernoulli principle? So I have mentioned the statement, and you can grow that mean analyze it. The sum of the pressure energy, kinetic energy, and the potential energy per unit volume for a non-viscous, incompressible, streamline flow of liquid is constant. So here we are just assuming the all the energy with respect to a per unit volume. Okay. So by the another two methods you can also do it that's per unit mass as well as per unit weight also. So here we are just assuming the method that is per unit volume. So how can we represent in the part of the mathematics this statement? Now this is the pressure energy per unit volume. This is the kinetic energy per unit volume, that is called the half rho v square. This is the potential energy per unit volume, that is called the rho gh, that is equal to the constant. Okay. So this is the proper that means statement of the Bernoulli theorem. And how we are just assuming the movement of a liquid through a pipe. So we are just applying a diagram here. Now here we are just imagining a cross sectional area of the pipe, those having the different, and we can assume here that a1 greater than a2 and through which we are just making the movement of a liquid. So the section a to a dash we have. So within delta t time it covers the length with the velocity v1, that is called the a to a dash. Okay. A to a dash we have, that is v1 delta t, and same how in the same time, that is delta t time, it covers the length, that is v2 delta t is there. As we are just imagining the liquid is incompressible, so the density of the liquid throughout the volume is constant. We have at the end A, or at the broader end, we have the pressure energy, that is called the per unit volume P1. Area of the cross section A1 we have, and for the simplicity we have assumed the density of the liquid at the end A, that is called the rho 1. Okay. Now at the end B, which is the narrower section we have, so here we have the density, that is called the rho 2 is there. P2 is the pressure energy we have, A2 is the area of the cross section we have. Now at the end A, the liquid having the height from the surface, that is called the H1, and at the end B, the height of a liquid, that is called the S2, which make the concept of the potential energy. Okay. Now due to the pressure variation, is liquid is flowing from one part to another part inside the tube. Okay. So how we are just making the calculation of the different types of the energy, and we are just putting them in the work energy theorem, or either you are just making the work done on a liquid, that is equal to the change in total energy, that is sum of the potential energy and the kinetic energy. So we are starting here the mathematical proof of this theorem. So here I am just using the concept that according to work energy theorem, the net work done on a fluid is equal to change in kinetic energy of fluid plus change in potential energy of fluid. So this is the one of the base equation we have, and according to it we are just doing the work. Okay. So here we are just using the concept of the equation of the continuity. So by use of equation of continuity, we are just writing that m1 is equal to m2, and we have made the changes that is called the m1 is equal to m2. So we are just making the possible changes by the formula, that means rho is equal to m upon volume, and m can be stated in the part of the rho into volume. Now m can be stated as rho v is the volume, that is called the area, into that mean length is there, so we are just compensating it by the v into delta t. Okay, so this is the simplest representation we have, and here we are just assuming the conservation of the mass is there. So whatever the facts, the whatever the formula we are using here, so it comes in the part that rho 1 a1 v1 delta t, that comes equal to rho 2 a2 and v2 delta t is there. Okay, so we can that mean cancel out the terms in the sense of the delta t and delta t. So whenever we are just solving it, so we are just getting a1 v1 that is equal to a2 v2, and we are just although assuming the rho 1 is equal to rho 2 for the incompressible liquid. So this is the one of the base equation we have. This is the equation number 1 we have. This is the equation number 2 we have. So how can we utilize them? We will find out. Now here we have to be make the assessment of the change in kinetic energy. Okay, so how can we write it? Now here I am just making the little bit changes. Already I have adopted the equation number 1. So this is the equation number 2, and this is the equation number 3 we have. So we can assume the change in the kinetic energy of fluid, that is equal to kinetic energy of the fluid at the B minus kinetic energy of the fluid at the A is there. So we are using the simplest formula, that is called m is the same for we have, that means I am just making that m v2 square by 2 minus m v1 square by 2, as I am just making the change taking the common of the, that mean m is there, so v2 square minus of v1 square we have, and is to be divided by 2, and we can submit the meaning of the m is there, either you are just writing the in the term of the rho 1 a1 v1 or delta t, or you are just writing in the term of and rho 2 a2 and v2 delta t is there. Okay, so here just I am assuming rho 1 rho 2 is equal to rho is there, so it will be the easier to me. Okay, as I can write at the place of the m a1 v1 delta t and the rho by 2 of that v2 square minus of v1 square. So it's the simplest representation of the, that mean change in the kinetic energy. This is the equation number 4 we have. Okay, now we can make the change in the potential energy. Change in potential energy of fluid, so it comes in the part of that potential energy at the B minus of potential energy at the A is there. Okay, so here we are just using the simplest formula, that is m, we have made the common mgh2 minus of mg of h1. Here we are just making the common of the mg is there, so it comes in the part of h2 minus of h1. Okay, so here we are just further making the representation of the mass is there, so I can write simply easily a1 v1 delta t rho and the g, and with the concern of h2 minus of h1. So this is the equation number 5, which make the concept of the change in potential energy of the fluid we have. So how we are just making the calculation of the change in the pressure energy. So I am just assuming the net work done, that makes the concept of the work done on the fluid at the A minus work done on the fluid at the B, because we are just making the concept as the fluid flows, so there is a loss of the energy, so the pressure energy at the end is more as compared to the pressure energy at the point B, and easily we can also assume that the movement of water inside a tube flows from the high pressure to low pressure region. Okay, so how we are just converting the work done in the term of the pressure. So I am just using that work done, that mean can be state in the part of the force into displacement we have. Okay, so there's the simplest representation of the formula we have, and we can make the change of the force, that mean in the part of the pressure into area is there. Okay, and the displacement can be in the state in the term of the concern of the, that mean velocity into delta t. So this is the simplest representation we have. So the net work done can be state, that mean work done at the A, that is called the P1 A1 and V1 delta T minus of P2 A2 V2 and delta T. So this is the simplest changeable formula we have used here. So this is the equation number 6, and what can we do? We are just using the equation number 4, 5 and 6 in the equation number 1, that is work energy theorem, that we have made the concept that net work done on a fluid is equal to the change in kinetic energy plus change in potential energy of the fluid we have. Now here we have the substitutions of the equation number 4, 5 and the 6 in the equation number 1, and whenever I am just substituting the equation number 6, so I am just also assuming by the use of the concept of the equation of continuity, that is called the A1 V1, that is we have used there, that is called the A1 V1 delta T is equal to A2 V2 and delta T, as we have assumed the rho 1 is equal to rho 2. So here just I am just assuming the at the place of the A2 I am just writing A1, at the place of the V2 I am just writing V1, and the delta T is the same. So I can easily take common these terms in all the steps. Okay, so whenever I am just making the common and cancelling out them, so it comes in the formation P1 minus P2, that is A1 V1 delta T, which I have made the common. Same I am just doing this one in the right hand side. Okay, A1 V1 delta T and bracket close is there, rho V2 square minus rho V1 square by 2 we have. Same how we have the plus rho G H2 minus of rho G of H1. Okay, so this is the representation we have, and same how we can cancel out these two terms from each other, and I can write the transformation of the terms, those are belongs to the portion A and those are belongs to the portion A is there. So the term 1 regarding to the portion A is there, and the term 2, okay, these are regarding to the all the types of the energy, those are at the portion B having the nomination in the subscript, that is called the 2 is there. So I am whenever I am just making the changes, so it comes in the portion or comes in the part that P1 plus rho V1 square by 2 plus rho G of H1, that is equal to P2 plus rho V2 square by 2 plus rho G of H2 is there. So as we are just making the comparison of this term, so we can easily state that as the liquid flows through a tube of a varying cross section, as we are just assuming the so many ideals concept here, that fluid is incompressible, fluid is non-viscous, and we are just assuming a streamline flow concept. So all the time by the concept of the equation of the continuity, we can say that pressure energy, kinetic energy, potential energy per unit volume is constant. So we can say P plus rho V square by 2 plus rho G H per unit volume is constant. Okay. So this is the proof of this statement. Now what are the some of the basic limitations of the Bernoulli principle? We can state them one by one. Now some basic facts about the Bernoulli principle, those we should keep in our mind. Now the first we have that Bernoulli principle applicable or the based on the concept of the conservation of energy, because already we have discussed the work energy theorem, that means the work done on a fluid that makes the change in the some of the energies are there. If the liquid is flowing through a tube where the H remain constant, then the P, we can write the Bernoulli theorem in the part of that pressure energy plus half rho v square. So it states that as we are just increasing the velocity of the liquid, so there is a decrease in the pressure we have. So we can easily state that V is inversely proportional to the P we have. Okay, so this is the another one concept we have. Now this theorem is applicable only for the ideal conditions. Okay, like the liquid having the zero viscosity, it should be the incompressible, streamlined flow is there, non-viscous flow should be there. Okay, so whenever we are just discussing the Bernoulli's principle, so it does not take the concept of the loss of the energy during the flow from the tube we have. Okay, so this is all about the Bernoulli principle. And further, we can recall the statement that pressure energy, kinetic energy, potential energy for a non-viscous, streamline, and incompressible liquid per unit volume is constant. You can make the that mean proving of this theorem by the help of per unit volume, per unit mass, or per unit weight, and all the contents which I have given to you. Just do it by your own and prepare it. It's a very good topic you have. Okay, thank you.